In the standard model of particle physics, the Higgs mechanism is essential to explain the generation mechanism of the property mass for gauge bosons. Without the Higgs mechanism, or some other effect like it, all bosons would be massless, but measurements show that the W+, W-, and Z bosons actually have relatively large masses of around 80 GeV, C2. The Higgs field resolves this conundrum. The simplest description of the mechanism adds a quantum field that permeates all space, to the standard model. Below some extremely high temperature, the field causes spontaneous symmetry breaking during interactions. The breaking of symmetry triggers the Higgs mechanism, causing the bosons it interacts with to have mass. In the standard model, the phrase Higgs mechanism refers specifically to the generation of masses for the W ± and Z weak gauge bosons through electroweak symmetry breaking. The Large Hadron Collider at CERN announced results consistent with the Higgs particle on March 14, 2013, making it extremely likely that the field, or one like it, exists, and explaining how the Higgs mechanism takes place in nature. The mechanism was proposed in 1962 by Philip Warren Anderson, following work in the late 1950s on symmetry breaking and superconductivity, and a 1960 paper by Yoichiro Nambu that discussed its application within particle physics. A theory able to finally explain mass generation without breaking. Gauge theory was published almost simultaneously by three independent groups in 1964, by Robert Brout and François Inglet, by Peter Higgs, and by Gerald Guralnick, R. Hagen, and Tom Kibble. The Higgs mechanism is therefore also called the Brout-Inglet-Higgs mechanism or Inglet-Brout-Higgs-Guralnick-Hagen-Kibble mechanism. Anderson-Higgs mechanism, Anderson-Higgs-Kibble mechanism, Higgs-Kibble mechanism by Abdus-Salam and Abid-Kaith mechanism, for Anderson, Brout, Inglet, Guralnick, Hagen, Higgs, Kibble and T. Hoof by Peter Higgs. On October 8, 2013, following the discovery at CERN's Large Hadron Collider of a new particle that appeared to be the long-sought Higgs boson predicted by the theory, it was announced that Peter Higgs and François Inglet had been awarded the 2013 Nobel Prize in Physics. Standard model. In the standard model, at temperatures high enough that electroweak symmetry is unbroken, all elementary particles are massless. At a critical temperature, the Higgs field becomes tachyonic, the symmetry is spontaneously broken by condensation, and the W and Z bosons acquire masses. Fermions, such as the leptons and quarks in the standard model, can also acquire mass as a result of their interaction with the Higgs field, but not in the same way as the gauge bosons. Structure of the Higgs field in the standard model. The Higgs field is an SU doublet, a complex scalar with 4 real components. Its U charge is 1. That means that it transforms as a spin or under SU. Under U rotations, it is multiplied by a phase, which thus mixes the real and imaginary parts of the complex spinor into each other, so this is not the same as two complex spinors mixing under U, but instead is the spinor representation of the group U. The Higgs field, through the interactions specified by its potential, induces spontaneous breaking of 3 out of the 4 generators of the gauge group SU times U. 3 out of its 4 components would ordinarily amount to Goldstone bosons, if they were not coupled to gauge fields. However, after symmetry breaking, these 3 of the 4 degrees of freedom in the Higgs field mix with the 3 W and Z bosons, and are only observable as spin components of these weak bosons, which are now massive, while the one remaining degree of freedom becomes the Higgs boson, a new scalar particle. The photon is the part that remains massless. The gauge group of the electroweak part of the standard model is SU times U. The group SU is the group of all 2 by 2 unitary matrices with unit determinant, all the orthonormal changes of coordinates in a complex 2-dimensional vector space. rotating the coordinates so that the second basis vector points in the direction of the Higgs boson makes the vacuum expectation value of h the spin or the generators for rotations about the x, y, and z axes are by half the Pauli matrices sigma x, sigma y, and sigma z, so that a rotation of angle theta about the z-axis takes the vacuum to, while the Tx and Ti generators mix up the top and bottom components of the spin or the Tz rotations only multiply each by opposite phases. This phase can be undone by AU rotation of angle 1/2 theta. Consequently, under both and SU Tz rotation and AU rotation by an amount 1/2 theta, the vacuum is invariant. This combination of generators defines the unbroken part of the gauge group, where Q is the electric charge, Tz is the generator of rotations around the z-axis in the SU, and Y is the hypercharged generator of the U. This combination of generators in a simultaneous U rotation by half the angle preserves the vacuum, and defines the unbroken gauge group in the Standard Model, namely the electric charge group. The part of the gauge field in this direction stays massless, and amounts to the physical photon. Consequences for fermions. In spite of the introduction of spontaneous symmetry breaking, the mass terms oppose the chiral gauge invariance. For these fields, the mass terms should always be replaced by a gauge invariant Higgs mechanism. One possibility is some kind of Yukawa coupling between the fermion field psi and the Higgs field phi, with unknown couplings g psi, which after symmetry breaking again results in the original mass terms, which are now, however, written in a gauge invariant way. The Lagrange density for the Yukawa interaction of a fermion field psi and the Higgs field phi is where again the gauge field A only enters d mu. The quantities gamma mu are the Dirac matrices, and g psi is the already mentioned Yukawa coupling parameter. Already now the mass generation follows the same principle as above, namely from the existence of a finite expectation value, as described above. Again, this is crucial for the existence of the property mass. History of research. Background. Spontaneous symmetry breaking offered a framework to introduce bosons into relativistic quantum field theories. However, according to Goldstone's theorem, these bosons should be massless. The only observed particles which could be approximately interpreted as Goldstone bosons were the pions, which Yoichiro Nambu related to chiral symmetry breaking. A similar problem arises with Yang-Mills theory, which predicts massless spin-1 gauge bosons. Massless weakly interacting gauge bosons lead to long-range forces, which are only observed for electromagnetism and the corresponding massless photon. Gauge theories of the weak force needed a way to describe massive gauge bosons in order to be consistent. Discovery. The mechanism was proposed in 1962 by Philip Warren Anderson, who discussed its consequences for particle physics but did not work out an explicit relativistic model. The relativistic model was developed in 1964 by three independent groups: Robert Broughton, François Inglet, Peter Higgs, and Gerald Guralnick, Carl Richard Hagen, and Tom Kibble. Slightly later, in 1965, but independently from the other publications, the mechanism was also proposed by Alexander Migdal and Alexander Polyakov, at that time Soviet undergraduate students. However, the paper was delayed by the editorial office of JETP, and was published only in 1966. The mechanism is closely analogous to phenomena previously discovered by Yoichiro Nambu involving the vacuum structure of quantum fields in superconductivity. A similar but distinct effect, known as the Stuka-Berg mechanism, had previously been studied by Ernst Stuka-Berg. These physicists discovered that when a gauge theory is combined with an additional field that spontaneously breaks the symmetry group, the gauge bosons can consistently acquire a non-zero mass. In spite of the large values involved, this permits a gauge theory description of the weak force. which was independently developed by Steven Weinberg and Abdus Salam in 1967. Higgs's original article presenting the model was rejected by Physics Letters. When revising the article before resubmitting it to Physical Review Letters, he added a sentence at the end, mentioning that it implies the existence of one or more new, massive scalar bosons, which do not form complete representations of the symmetry group. These are the Higgs bosons. The three papers by Brout and Inglet, Higgs, and Guralnik, Hagen, and Kibble were each recognized as milestone letters by Physical Review Letters in 2008. While each of these seminal papers took similar approaches, the contributions and differences among the 1964 PRL symmetry-breaking papers are noteworthy. All 6 physicists were jointly awarded the 2010 J. Sakurai Prize for Theoretical Particle Physics for this work. Benjamin W. Lee is often credited with first naming the Higgs-like mechanism, although there is debate around when this first occurred. One of the first times the Higgs name appeared in print was in 1972 when Gerardus T. Hooft and Martinus J. G. Veltman referred to it as the Higgs-Kibble mechanism in their Nobel-winning paper.